we are going to discuss the mathematical models of quantum mechanics, the mathematical representation of quantum mechanics. This is the continuation of the previous video lecture. Quantum mechanics lives in Hilbert space. It is an n-dimensional abstract space. Any quantum particle is represented by a vector which can be real number and a complex number. These vectors are elements in the Hilbert space. So there exists a dual space in which for every vector corresponding complex conjugate exists. A normal vector is denoted by a Keck notation and its complex conjugate vector is denoted by a Braun notation. These notations were introduced by Paul Dirac. The Keck vectors are column vectors and the Braun vectors are row vectors. This matrix representation leads to matrix mechanics, and they are equivalent to wave mechanics. The vector addition and the scalar multiplication are the main properties in the Hilbert space. We shall discuss linear vector space now. A linear vector space has two sets of elements and two algebraic rules. A set of vectors psi, chi, phi, del, lambda. So those elements are called vectors. And set of scalars a, b, c, d, and goes on. A rule for addition and the rule for multiplication, which are followed below. The first one is addition rule. If psi and chi are vector elements of a space, their sum chi and psi is also a vector in the same space. Commutative property. Psi plus chi, which is equal to chi plus psi. Associative property. Chi plus psi plus phi, which is equal to psi plus chi plus phi. 0 are natural vectors. 0 plus psi equal to psi plus 0, which is equal to psi. Sum of inverse of a vector, psi plus minus psi, which is equal to minus psi plus psi equals 0. Multiplication rule. The product of a scalar with a vector gives another vector, that is a psi, which is equal to chi. In general, if psi and chi are two vectors in the space, any linear combination a psi plus b chi is also a vector in the space. Here a and b are scalars. Distributive property. A multiplied by psi plus chi, which is equal to a psi plus a chi. Associative property. A b psi equals a b psi. Each element psi there exists a unitary element I and zero scalar such that I psi, which is equal to psi I, which is equal to psi. 0 psi, which is equal to psi multiplied by 0, which is equal to 0. 0 multiplied by psi, which is equal to psi multiplied by 0, which is equal to 0. Linear independent and dependent of vectors. A set of n vector u1, u2, u3 is said to be linearly independent if there exists no relation between them. If one vector is represented in terms of another vector, what we call this is linearly dependent vector. If one vector cannot be represented in terms of another vector, linearly independent vectors. For example, C1 U1 plus C2 U2 plus Cn Un, which is the vector P. Here, one vector does not depend on the other vector. Whereas, if C1 U1 plus C2 U2 equal to 0, then this expression can be simplified as U2 equals minus C1 by C2 times U1. So here, this vector can be written in terms of another vector. So they are all linearly dependent and implies that one depends on the other. And the maximum number of linearly independent vectors is the dimension of the vector space. Basis vector. Consider a set of n linearly independent vectors psi1, psi2, psi n then any arbitrary vector psi in the space can be expanded as capital Psi equals C1 psi1 plus C2 psi2 plus dot 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 Cn psi n, which is equal to summation over I equals 1 to n Ci psi I. Here psi I is known as a basis vector and Ci are the expansion coefficient, which are called components of the vector psi. Equation 2.40 represents the linear combination of basis vectors, just like superposition of two elements, two states in the vector space. Basis consists of a maximum possible number of linearly independent vectors. These basis states form a vector space over real and complex numbers. Linear operators. Here we have a linear combination of basis states. Linear transformation exists. These operators are nothing but linear operators. We can write the expansion theorem as psi, which is equal to sigma over I equals 1 to n Ci psi I. We will introduce this notation very shortly, and this is represented as the ket notation, ket psi, which is equal to sigma over I equals 1 to n. Ci is the expansion coefficient, and this is ket small psi I. We will introduce this ket notation shortly. We know that any quantum state is the linear combination of basis states. Any quantum state lives in vector space if the inner product is defined. So inner product is the main property for any linear vector space. Then the vector space is called as Hilbert space. Hilbert space is spanned by basis vectors. For example, when you take a spin-off system, which is spanned by two basis states. One is spin up, another one is spin down. So when you are going to have an electron, this will have linear combination of both spin up and spin down. The moment when you are going to measure, this will show spin up or spin down. Suppose when you take a spin 1 system, which is spanned by three basis states, 1, 0 and -1. This expression, what we call this as linear transformation equation. A cap, this is called a cap. A cap means A is an operator. Operator can be subtraction, differentiation, integration, addition. So those things are called operations. So A is an operator, operates on psi, will give another vector, that is psi prime. This transformation from one system to another system is linear transformation. The transformation from one state to another state is called linear transformation. The mathematical definition for linear operators is defined as O operator operates on the combined system is equal to operator operates on the individual system. That is, O operator operates on psi1 plus psi2, which is equal to operator operates on psi1 plus operator operates on psi2. So these operators are linear operators. Operator to be linear should satisfy two properties. One is additive and homogeneity. Additive means just now we have seen A operator operates on the combined system, which is equal to operates on the individual system. So these are all ket vectors, and these ket vectors, they belong to linear vector space. Homogeneity says a vector, an operator, this is C is a scalar, both operate on psi, when we can pull this scalar out. So this is called a scalar multiplication. So C times A operator operates on psi. Similarly, if you have two operators, A and B, A plus B operator operates on psi, which will give us A operator operates on psi plus B operator operates on psi. So they come under linear operations. Here A and B are linear operators. And A operator operates on B psi, which is equal to AB together operates on psi. And of course B operator operates on psi will give us psi prime, which you have seen earlier. So we can write this equation as A operator operates on psi prime. Linear operators. So definition for linear operator is nothing but these two conditions. One is scalar multiplication, another one is addition. An operator O is a linear operator if any arbitrary operators psi1 of x and psi2 of x with the following two conditions. Operator operates on the combined system will give us operator operates on the individual system, and this is about a scalar multiplication. So you can pull scalar out. In quantum mechanics, observables such as position, momentum, angular momentum, energy, and many others are represented by linear operators. For any operator, we can write the following equation. O operator operates on psi, which will give us the value, O value, with a wave function. Psi is the wave function. Here psi is the wave function. O is the eigenvalue. And O cap, O small cap, this is called an operator. If the same wave function is obtained, then this wave function is called eigenfunction. So here, left hand side you can find psi, and right hand also you can find psi, and this wave function is nothing but eigenfunction. This equation is known as eigenvalue equation. The mathematical operations such as differentiation, integration, addition, subtraction, squaring, all those things are called operators. It is defined as a rule by which a different function is obtained when an operator operates on any given function. So, C operator operates on any function will give us another function, g of x. For example, we can just take differentiation on an operator. So, d by dx of f of x equal to g of x. For example, d by dx of x squared equal to 2x. Here x squared is the one function, x is the obtained function, 2 is nothing but the eigenvalue. This equation is known as the eigenvalue equation. And the operation for this, d by dx of psi1 plus psi2, which is equal to d psi1 by dx plus d psi2 by dx. This operation is nothing but linear operation. When the operator is linear, it is defined as A operator operates on the combined system will give us operator operating on the individual system. Further, the operator which squares the squaring the operator. You are taking the square root of the operator. They are not linear operators. Suppose when you are going to have the linear operator, the condition is like this. The condition is this one. So psi1 plus psi2 whole square is not equal to psi1 squared plus psi2 squared. Similarly, taking the root of psi1 plus psi2 is not equal to root of psi1 plus root psi2. So taking the squares and taking the square root, they are not linear operators. Linear vector space. We know that the vector is a physical quantity having both magnitude and direction. The vector of magnitude is called a unit vector, which represents an arbitrary vector. The unit vectors I, j, and k lie along positive direction of three mutually perpendicular axes. Then any vector can be represented by y equals c1i plus c2j plus c3k. Here c1, c2, c3 are unit vectors. I, j, k are said to form a basis for a set of all vectors in 3 dimensions. Since these unit vectors are mutually perpendicular directions, we can say that they form an orthogonal basis I, j, k. C1, C2 or C3 are scalars and their components I and j and k are basis vectors. We may represent y as a column vector as y equals y1, y2, y3 in terms of column vector, and the components of I will be 1, 0, 0, j will be 0, 1, 0, 3 dimension, k will be 0, 0, 1. Hence the basis vectors are written as a column vector as I equals in a column vector 1, 0, 0, j cap which is equal to 0, 1, 0, and k cap equal to 0, 0, 1. The properties. Addition is commutative and is written as a plus b which is equal to b plus a. Addition is associative and is written as a plus b plus c which is equal to a plus b plus c. The product of two vectors such that ab operates on the function f of x which is equal to a b operator operates on f of x. Multiplication is associative and is rewritten as a operator operates on b plus c which operate on f of x which is equal to ab plus AC operator operates on f of x. Commutative of operator A and B is denoted by with this bracket A comma B, what we call the commutative bracket A comma B, which is defined as A comma B, which is equal to AB minus BA. There are two conditions. If the commutative bracket AB equals 0, it implies that the operators A and B are set to commute with each other. It means that they can be measured simultaneously. And second condition is A comma B is not equal to 0. So it implies that AB plus BA equals 0. So it implies that the operators A and B are said to anti-commute with each other. And for the inverse, A inverse equals A inverse A, which is equal to I. I is the unit vector. Eigenfunction and eigenvalue. An operator A operating on any function will give a function multiplied by a constant, so called as eigenvalue of the operator. This equation is known as eigenvalue equation, and it is expressed as A operator operates on the function will give us A value with the function. If these two functions are the same, then what we call this eigenfunction, and A is nothing but eigenvalue. This A cap is nothing but an operator. Here A is the eigenvalue of the operator. The function psi of x is called the eigenfunction of the operator A, corresponding to the eigenvalue small a. For example, the operator d by dx operating on e power kx will give the eigenvalue k, and it is given by d by dx of e power kx is equal to k times e power kx. So e power kx is the eigenfunction, k is the eigenvalue, d by dx is the operator. In general, we have a set of values small a for which eigenfunctions exist. Then we can write the eigenvalue equation as. So this is for a single particle. If there exists m number of particles, we can write A operator operates on psi m of x, which is equal to am psi m of x, where m equals 1, 2, 3 goes on. The same eigenvalues are obtained for different wave functions. Then the eigenvalues are said to be degenerate. For each wave function and each value exists, we call this as non-degenerate. Suppose if there are many wave functions, there exists a single eigenvalue, we call this as degenerate. If all the eigenvalues of operator are discrete, it is said to have a discrete spectrum. Some properties of operators are as follows. O operator, here it is the squaring. So O operator, the square of the O operator operates on f of x. We should write like this. First O operator, we'll have to separately write O operator, again one operator operates on f of x. First the second operator, we should operate on the function f of x, will give us eigenvalue, which is nothing but O. Now O is a value, we can pull it out. So this equation can be written as, we can pull it to O out, and another operator operates on f of x will give us another O. So O multiplied by O, these two are values, which is nothing but O squared. So O squared, the operator O squared operates on f of x will give us the value squared in times f of x. Eigenvalue equation is given by A operator operates on psi, which is equal to lambda psi. For example, just take get psi, which is equal to pi by 2. So phi 2. Get psi, the column vector phi 2. For example, suppose if we take A, operator A is a matrix element, which we'll see later. It's a matrix, it's a representation of operator A in terms of 2 by 2 or 3 by 3 or 4 by 4 matrix. And here it is written as 1, 2, 3, 4. And this operator operates on the column vector 5, 2, which will give us 9, 2, 3. So this is exactly similar to operator A operates on psi will give us 5. Another column vector. Here this is one column vector, and this matrix operates on one column vector will give us another column vector. Suppose when you are going to take this A matrix, A operator like this, then your psi is 5, 2. The answer is 15, 6. You can pull 3 you can pull 3 out, both common. So 3, 5, 5, 2. We can write 3 column vector 5, 2. And this is exactly similar to, this is your 15, 6 is nothing but your psi. Whereas 3, 5, 2 is nothing but lambda psi. See, here lambda psi. So this can be written as A operator A acts on psi will give us lambda psi. This is exactly like stretching and expanding. So 3 times it has been expanded. 3 times it has been expanded. That 5 to 15, 6 can be written as 3 times 5 2. So 3 times it has been stretched, expanded. Now we will concentrate on dual space. Dirac-Brown-Ket notation. The quantum matrix theory can be done in a compact form of making use of notations discovered by Dirac. It is a useful notation due to Dirac, which is commonly used for any Hermitian unitary operator and state vectors. According to his ideas, each dynamical state is represented by a certain type of vector known as ket vector, or simply ket denoted by a symbol psi, represented by a column vector. So this representation is nothing but ket, so ket psi, which is nothing but a column matrix, column vector. Correspondingly, its complex conjugate is represented by a bra vector, which is denoted by this symbol, bra psi. And this is represented in terms of row matrix, row vector. And the vectors of dual space are called bra vectors. This dual. So the dual for ket is bra and dual for bra is ket. These two dual space exist in linear vector space which live with Hilbert space. Two spaces, ket notation and its corresponding complex conjugate bra notation are dual to each other and vice versa. These symbols are referred as ket and bra notations and famously known as ket-bra algebra. There exists one-to-one correspondence between the vectors of bra and ket spaces. Ket and bra vectors thus associated by the one-to-one correspondence are said to be conjugate to each other. The kets form a linear vector space, and any linear combination of several ket vectors is also a ket vector. The connection between dual space is given by the scalar product of a bra vector and a ket vector, such that the scalar product of two vectors, bra phi and ket psi, in the new notation becomes. Now we know that this is the normalization condition which you have written already, which we discussed earlier. So integration of pi star psi d tau, this is represented in terms of wave mechanics, which can be written as, and phi star is nothing but bra phi, and your psi is denoted as ket psi. And this representation wave mechanics can be replaced with this notation, what we call this as ket-bra notation, phi with psi. And this is ket psi is, already we know that ket psi is represented in terms of column vector and bra phi is in terms of written in terms of row vectors. So this is exactly phi psi can be written as phi 1, phi 2, phi 3 and phi 1, phi 2, phi 3. And this is matrix representation. And this is exactly like an inner product. So this is nothing but inner product. And this is called a matrix mechanics. So matrix mechanics in which broad set notations exist. We'll get a number. So the answer for this is nothing but a number. Similarly, the matrix element of A is given as Aij, which is equal to A sandwiched between phi j and psi I star. And of course, this is a normal one. This is the corresponding complex conjugate, which can be written in terms of Dirac notation as bra psi I and A is the operator and ket phi j. So operator sandwiched between ket phi j and bra psi I. And we know that the scalar product phi psi, which is equal to psi complex conjugate. So, as I said earlier, the complex conjugate of bra is nothing but ket. The complex conjugate of ket is nothing but bra. So, when you're going to interchange, you have to go with a star complex conjugate. All the ket vectors of the system and the bra vectors in the dual space together form a linear vector space which live in Hilbert space. Properties of bra and ket notation. Operation on a ket vector from the left with an operation produces another ket vector. So A operator operates on ket psi will give us ket phi, another vector. And the operator A operates on bra vector similarly, and the operator produces another bra vector, represented by equation 2.69. The kets may be multiplied by the complex number and may be added to give another kets. A1 operates on ket Q plus A2 with ket R which is equal to ket S. A1, A2 are two complex numbers. The sum of two bra vectors acting on ket vector Q is the sum of individual bra vectors acting on Q. For example, R plus S with ket Q which is equal to, we can write this as individually as RQ plus SQ. The expectation value of operator A in the state can be written as any expectation value is nothing but sandwich between normal vector and its complex conjugate. So in bracket notation, this can be written as like this. So A sandwich between ket psi and bra psi. The eigenvalue equation of an operator A operating on psi is given as A operator operates on psi will give us lambda psi. Here ket psi is an eigenket operator and lambda is the eigenvalue. It's a eigenket. This is eigenket. Operator A. This A is an operator. A set of eigenkets such that ket psi 1, ket psi 2, ket psi 3, ket psi n. This is ket psi m. And it is orthogonal to the set of following orthogonality condition. And we know that this is the inner product bra psi n with ket psi m which is equal to delta mn. And delta mn is nothing but Kronecker delta function. And of course, if m equals 1, m equals n, the answer is 1. If n is not equal to m, answer is 0. When the scalar product is 0, then the bra and ket vectors will be orthogonal. Suppose if they are equal, we have what we call this as normalized. For a complete set of eigenstates, psi I, bra psi I, which is I equals 1, 2, 3 goes on. So we can express any ket vector with the expansion theorem. So capital psi, ket psi which is equal to sigma over I equals 1 to n Ci times psi I, ket psi I. If a bra vector is put on the left on the ket vector, it forms a scalar product. So this is nothing but a scalar product. If a bra vector is put on the right side, on the other way around, right side of the ket vector, it forms the operator and this is called completeness. So what we call this is completeness in quantum mechanics, and it is given by this notation. So it is ket psi n with the bra psi m. So what we call this is outer product. If both the indexes are the same, for example, just take sigma over n equals 1 to infinity, psi n with psi n. So if here both the indices are same, what we call this as projection operator. The answer is I cap, where I is the unit vector, and when the unit vector acts on uniket, it leaves the ket unchanged, that we know already. So I operator operates on psi will give us same psi. In summary, a linear operator is a fundamental concept used to describe the behavior of quantum systems and their evaluation over time. It plays a central role in representing physical observables, transformations, and equations of motion in quantum mechanics. They play a crucial role in the formulation and understanding of quantum mechanics and are used to calculate the probabilities of measurement outcomes, study quantum dynamics, and analyze quantum systems properties. Dirac notation introduced by Dirac. And of course, we know that this is ket notation, and this is will be bra notation. So ket notations are column vectors, bra notations are row vectors. For example, we take psi, and this can be written as ket psi, and corresponding complex case is nothing but psi star, which is represented in terms of bra psi. The conjugate of ket is bra, and the conjugate of bra is ket. So A psi. See here we have A psi. A is a scalar. You can pull it out. So A ket psi. And similarly, bra A psi is equal to, and this is the complex conjugate of psi. So this must be written as A star bra psi. And of course, A psi together, ket psi whole star, which is equal to A star bra psi. Matrix representation of bra and ket operators. Any ket vector is represented as a column vector, we know already. So ket psi, which is equal to, in terms of column vectors, column matrix psi 1, psi 2, psi n. Similarly, corresponding bra vectors will be in terms of bra vectors. So your phi, which is equal to phi 1 star, phi 2, phi n. If two vectors phi and phi, then the scalar product of these two functions, see, these two functions, nothing but this is your bra and ket notation, and this is wave mechanics representation. And of course, we know that we are going to interchange the bra with ket with bra, that it was complex conjugate. Now we will solve a simple problem. Psi 1 is given as psi 1, ket psi 1. So this is a column vector, column matrix 1, 2, 3, 8. And psi 2 is nothing but in terms of column matrix 1, 1, 2. And one can find out bra psi 1 taking the complex conjugate. So column into rows. So bra psi 1 becomes 1, 2, minus 3, 8. Similarly, psi 2 becomes, bra psi 2 becomes 1, 1, 2. Now we will calculate psi 1, psi 2. That is bra psi 1 with ket psi 2. And we know that psi 1 and psi 2. Look over here. We have 1, 2, 3, I, 1, 1, 2. See here 1, 1, 2, 3, I. See here 1, 2, 3, I. Here it is 1, 1, 2. So ordinary matrix multiplication will give us 3 minus 6i. So psi 1, psi 2 is nothing but 3 minus 6i. Similarly, when you are going to interchange psi 2 with psi 1, that is bra psi 2 with ket psi 1, we can write this as 1, 1, 2, 1, 2, 3i will give us 3 plus 6i. So 3 plus 6i. And of course, we know that bra psi 1 with ket psi 2 is equal to the complex conjugate of bra psi 2 with psi 1. See here 3 minus 6i, the complex conjugate of 3 minus 6 is nothing but 3 plus 6i. So it is exactly equal. Then the complex relation for the basis vector is given as equation 2.87. And of course, if psi star is equal to psi, then we can say that mod psi squared, which is nothing but square interval function. This value should be always less than infinite. Now we know that the completeness is given by this condition, which is equal to I. And suppose if we are going for the same problem, then the column matrix is given as 1, 1, 2, and the row matrix is given as 1, 2, minus 3i. Then we can have a matrix. See, 1 multiplied by 1, 2, minus 3i, 1 multiplied by 1, 2, minus 3i, this row vector, second row vector, and 2 multiplied by 1, 2, minus 3i will give us 2, 4, minus 6i. So, when bra vector multiplied by a column vector, when a bra vector multiplied by the ket vector will give us another matrix. It's an operator. And another one diversion is race of outer product is the inner product. Race of ket psi 2 with bra psi 1 equal to inner product. Bra psi 2 with ket psi 1. Where I is a unit vector, and when the unit operator acts on any ket, it leaves the ket unchanged. So which is given as this condition. And we know that psi equals I psi. We know already. Instead of psi, you substitute this expression. So we can substitute this expression. And what if these two, psi n with psi? psi n with psi is nothing but a number. Number can be written anywhere. See, this is a vector, and of course, if we multiply bra psi n with ket psi, it will give us number. So I can pull this term alone out. So that will give us bra psi n with ket psi multiplied by n summation over n equals 1 to infinity psi n. And this can be written as psi n psi, this can be written as, and of course we know that ket psi is nothing but summation over n equal to 1 to infinity Cn psi n. Okay. So Cn is nothing but number. So Cn is equivalent to bra psi n ket psi, and which represents the projection of psi on psi n. So bra psi I psi j, which is equal to del ij. And if both the things are equal, I equals j, normalized, I is not equal to j, it's a perpendicular to each other complex conjugate. Del ij is called as a Kronecker-Delta symbol. Psi I and psi j are orthonormal. Orthogonal plus normal, orthonormal. The base is said to be complete if it spans the entire space. Definition for Hilbert space. This is the linear vector space, usually denoted as infinite dimension and complex, such that all infinite series will be convergent. A linear vector space over a complex number whose inner product is defined. So whenever there is in linear vector space, main condition will be inner product. It should define inner product. Hilbert space is spanned by basis vectors capital psi equals C1 psi1 plus C2 psi2. So it means that there exists two bases. The dimension is 2. So dimension depends on the basis. The transformation from one state to another state will be linear. For every ket vector, there exists a bra vector. Dual space of Hilbert space, kets and bras are the elements in the Hilbert space. Properties of elements in the Hilbert space. H is a linear space. It is complex and of countable infinite dimensions, such that all infinite series occurring in it are convergent. In quantum mechanics, we often deal with complex functions, and the corresponding Hilbert space is that of quadratically integrable, which is nothing but complex function. A state function psi contains all the physically relevant information about the physical system at a given instant of time and is represented by a vector along a direction in the Hilbert space. If psi represents a physical state, then a constant multiplied by psi, then both represent the state. Therefore, the arbitrary representative vector of the wave is normalized to 1. The scalar product will be always positive, and the last property is the coefficients, expansion coefficients, C1, C2, Cn represent the components of the vector psi in the Hilbert space. Matrix representation of a wave function. Consider a complete orthonormal set of wave functions psi1, psi2, Cn, which form the basis of the coordinate system in the Hilbert space. The expansion theorem states that psi can be expanded in terms of the function like this. So your ket psi, which is equal to summation over I equals 1 to n Ci psi I. I'm going to multiply on both sides by bra psi I. So this equation becomes bra psi I, capital psi, capital ket psi, which is equal to summation over I equal to n Ci. So bra psi I with ket psi I. And of course, we know that this answer is 1. Bra psi I with ket psi is answer is 1. So which is equal to Ci. So Ci can be written as bra psi I capital psi. See, psi 1, bra psi 1 with the capital psi in terms of matrix. Bra psi 2 with capital psi bra psi n with the capital psi, which is equal to C1, C2 Cn, which is nothing but capital psi. Where the coefficient Ci, which is equal to bra psi I psi, represents the projection of psi onto psi I, is a component of psi along the vector Ci bra psi I. So a set of its components C1, C2 Ci along bra psi 1, bra psi 2 psi n. Matrix representation of an operator. Consider a dynamical variable whose operator A transforms a function psi into another function phi. For example, A operator operates on phi will give us capital psi. In terms of basis function, we can write psi which is equal to expansion. This is expansion theorem. Capital psi which is equal to summation over I equals 1 to n Ci psi I. So as I said earlier, multiplying on both sides by bra psi I will give us this, and of course psi I will give us answer is 1. So Ci equals bra psi I with capital psi. Similarly, any expansion theorem, another wave function phi can be expanded in terms of j equals 1 to n summation over dj phi j, multiplying on both sides by bra phi j. So bra phi j, phi which is equal to summation over I equal to 1 to n dj, then bra phi j get phi j, and of course the answer for this is 1. So dj which is equal to bra phi j get phi. Now substitute equation 2.92. This is 2.92 and this is 2.93 is here. This is equation 2.91. So we can substitute. So instead of psi, you substitute Ci psi I. So Ci psi I, which is equal to A as it is A. Instead of phi, you substitute dj phi j. So dj phi j. Multiplying on both sides by psi I. So Ci psi I which is equal to dj psi I A phi j. And of course we know that psi I which is equal to 1. So Ci equals this one. And dj psi A phi A, so which is equal to dj, and this is what this can be represented in terms of matrix element. So A operator operates on A operator sandwiched between ket phi j and bra psi A is nothing but a matrix element. So which is represented in terms of Aij, which is equal to A11, A12, A1n, and A21, An1, and up to Ann. So Aij is nothing but a matrix element. And of course, C1 can be written as, Ci can be written as C1, C2, Cn. Dj can be written as D1, D2, Dn. So this is a matrix representation of any matrix Aij, any operator. So Aij which is equal to A operator operates sandwiched between ket phi j and bra psi I. Here Aij is the matrix element which forms the elements of the matrix. It is a square matrix. This matrix is equivalent to the complete specification of the matrix A. So A equals A11 A1n up to Ann. And of course, use the Kronecker delta function condition. If I equals j, answer is 1. If I is not equal to j, answer is 0. So look at here, all the diagonal elements, I equals 1, I equals j. For example, we take diagonal elements. Here it is I, this is j. So I equals j. Here also I equals j. And here also I equals 0. All the diagonal elements exist. Rest of the elements, of diagonal elements, positive and negative side, it will become 0. So each Hermitian operator has a matrix representation as a diagonal matrix, provided the wave function is expanded in terms of eigenfunctions. So operators determine the eigenfunctions. Physical meaning of matrix element. Matrix elements obey the rules of addition, subtraction, multiplication, associative, and distributive. The following important properties of operators are needed in quantum mechanics. Consider a Hermitian operator. So in quantum mechanics, operators are Hermitian because they give real values. So Aij is nothing but A sandwiched between ket psi j with bra psi I. And we know that A operator on psi j will give us Ai psi j. We can pull Ai out. It's a value. So Ai bra psi I ket psi j which is equal to Ai del Ij which is equal to Ai if I equals j. The resulting matrix is diagonal because I equals j. only diagonal elements alone exist and they are real because we have taken the Hermitian operators. This leads to an important result that the matrix representation of an operator with respect to its own eigenfunction can be written in terms of matrix elements, and the diagonal elements are given values or eigenvalues of operators. So Aij, which is equal to A operator sandwiched between psi get psi j with bra psi I, and we are going to interchange bra with get with bra. You have to go only with a Hermitian, and of course A operator also will become Hermitian, but Hermitian operators are real values, so A which is equal to A dagger. Here the diagonal elements I and j, I equals j, are real, and half diagonal elements on either side will be complex numbers or complex conjugate. Psi i's form a complete set of functions, and A is the Hermitian operator. The matrix represents the operator as Hermitian. Since the outcome of an experiment to measure a real observable must be a real number, Hermitian matrices would represent such observables as their eigenvalues are real.